Systems of linear equations and augmented matrices, definitions and relationships. The process of solving systems of equations by elimination and substitution is efficient as long as we have a small number of variables and a small number of equations. However, as this grows, we get more variables, more equations, this gets harder and harder. So we can make this process more efficient for generalization purposes and computer work by using a rectangular array of numbers written within brackets called a matrix. And here are two examples of matrices. Matrix A we see is 2 rows and 3 columns. Matrix B has 3 rows and 3 columns. Each number in a matrix is called an element. The size of a matrix is determined by the number of rows and the number of columns. We let the letter M represent the number of rows and N represent the number of columns. And we say that the size is M by N. And we let a multiplication symbol or a lowercase x represent the word by when we write this. So the size of a matrix is written M times N. So how many elements does matrix A have and what is its size? If we consider matrix A, we see that we have elements 1, -4, 5, 7, 0, -2. So there are 6 elements in matrix A. We see that there are 2 rows and 3 columns, so matrix A is a 2 by 3 matrix. A square matrix is a matrix that has the same number of rows and columns. Matrix B is an example of this because it is a 3 by 3, 3 rows and 3 columns. A column matrix is a matrix with only one column, but it could have an infinite number of rows. Similarly, a row matrix is a matrix with only one row, but it could have an infinite number of columns. Our matrices A and B appear here again. We're going to continue to use these to help us define some more things and look at some more examples. The position of an element in a matrix is given by the row and column containing it. We denote the position by A sub I, J. I represents the row containing the element, J represents the column. The elements A sub 1, 1 and A sub 2, 2, or we can say A1, 1 and A2, 2, make up the principal diagonal of matrix A. So this is just saying that we're looking at the element A1, 1 being the element in row 1, column 1, and A2, 2 is the element in row 2, column 2. And in general, that is how we find the elements in the principal diagonal. They will be A1, 1, A2, 2, A3, 3, A4, 4, A5, 5, and so on. So we're going to identify the element A sub 1, 2 in matrix A. So we want the element that is in row 1, but in column 2. So row 1, we have 1, -4, 5. So the element A1, 2 is -4. Now we're going to identify the elements of the principal diagonal of matrix B. So we're looking for row 1, column 1, row 2, column 2, row 3, column 3. So we have -4, 1, and 9. Matrices serve as a shorthand when solving systems of linear equations. So associated with the system 2x minus 3y equals 5, and x plus 2y equals -3, we can find coefficient, constant, and augmented matrices. So let's do that for this system. So what we're going to do, For the coefficient matrix, this is just going to be the coefficients of x and y in each of our equations. So we're going to let column 1 represent x and column 2 represent y. So in our first equation, we have 2x, negative 3y. So row 1 in the coefficient matrix is 2, negative 3. Row 2 will be 1, 2, because we have 1x and 2y. The constant matrix is going to represent what each equation is equal to. So because the first equation is equal to 5, 5 is going to go in row 1, and negative 3 is what the second equation is equal to, so that's going to go in row 2. The augmented matrix takes the coefficient matrix and the constant matrix, and it puts it in one big matrix, and it separates the coefficient and the constant by a bar. So we can think of this bar as equals. So here we have 2x minus 3y equals 5, and that is row 1, and that is the first equation. So let's write the coefficient matrix and the augmented matrix of the system 7x1 plus 6x2 equals 4, and 4x1 minus 9x2 equals 9. So we're going to let column 1 be x1 and column 2 represent x2. So the coefficient matrix is just the coefficients of the x1 and x2. So in row 1 we have 7, 6, because we had 7x1 plus 6x2. Row 2 we have 4, negative 9. The augmented matrix is going to take the coefficient matrix we just found, and it is going to pair it with the constant matrix, or what each equation is equal to. So we see that we get an additional column, 4, 9, and we separate that with a bar. Now, an augmented matrix can be transformed into a row equivalent matrix by performing row operations. One row operation that we can do is interchange rows. So we represent this by Ri interchange with Rj. The interchange is represented by a double-headed arrow. We can multiply a row by a non-zero constant k. So the row command for that is in parentheses. Kri replaces Ri. A constant multiple of one row can be added to another. So for example, Krj plus Ri replaces Ri. So given the matrix with row 1, negative 3, 2, 4, negative 6, negative 8, and notice this is an augmented matrix. We know that because we have the bar. Some texts will use a dotted or dashed line. I'm using a solid here. For A, this double-headed arrow means that we want to interchange row 1 and row 2. So because 1, negative 3, 2 is row 1, we're going to switch it with row 2. So our new matrix has 4, negative 6, negative 8 in the first row, 1, negative 3, 2 in the second row. So now let's look at what happens if we perform the command negative 4 row 2 plus row 1 to replace row 1. So notice that we are replacing row 1. That means that row 2 is staying the same. So we could go ahead and we could write that down. So now we have to figure out what our new elements in row 1 are. So to do that, we're going to look at each column, and we're going to say negative 4 times the element in row 2 in that column, and we're going to add it to the element in row 1 in that column and get a new element. So negative 4 times 4 added to 1 gives us negative 15. So that is now the element in row 1, column 1. Negative 4 times negative 6 minus 3 is 21. So that's the next element in the new row 1. And negative 4 times negative 8 plus 2 is 34. So that's the new element in row 1, column 3. The identity matrix is a square matrix with ones along the principal diagonal and zeros everywhere else. So for example, the identity matrix of order 2 is a 2 by 2 matrix with row 1 being 1, 0 and row 2 being 0, 1. And the identity matrix can be very useful in solving augmented matrices. If we look at the augmented matrix 1, 0, 5, 0, 1, negative 2, if we say that column 1 represents the variable x1 and column 2 represents the variable x2, then I can actually write this as a system of linear equations where I have 1x1 plus 0x2 equals 5 and 0x1 plus 1x2 equals negative 2. So I know that x1 is 5 and x2 is negative 2. So that is my solution.